the playing of that song at another date. What's funny, though, is there's another pun, if you will, a direct comparison to that song with what we're going to talk about today. One of the results that we're going to talk about today, they actually spoke about in that song having a piano up my nose. Who sang that? What are we going to talk about today? Uncle Lee here with you. I do not have a piano up my nose, but I am going to talk about the P-series test, which is a simple test. A P-series test to determine if a particular series converge or diverge. And we've talked about how many different tests there are. This is a rather straightforward test. And it has some applications. One of the applications of the P-series test is going to be the limit comparison test or the direct comparison test. So these are two important applications of the P-series test. P-series test 101, fairly simple. So where are we going to start? What we're going to do is we're going to start here and we're going to examine three improper integrals. And keep in mind, at this stage in your calculus career, you should have studied already improper integrals, and I know that we have. So I'm going to look at three simple examples of improper integrals, and I'm going to go kind of quick through these examples so I can get to the series test involved with them, the relationship there. And so I have this improper integral from 1 to infinity of 1 over x dx, which is equal to the limit as b goes to infinity of the definite integral from 1 to b of 1 over x dx. B is a real number, and we're taking b as going to infinity here. We know that the antiderivative of 1 over x, we know that's ln of absolute value of x. B is, everything's positive over here because we're taking b as it goes to infinity, so we're only talking about positive things. So this limit here is going to be, this is going to be ln of b minus 0, and as the limit is that b goes to infinity, ln of b is going to continue to grow. ln is an increasing function, and we've seen in pre-calculus that ln grows slowly, but it does grow. So this dude right here, this limit diverges, therefore this particular improper integral from 1 to infinity 1 over x dx diverges. We've done that. That's a very simple improper integral that we certainly have looked at before. Let's look at the example number 2 of improper integral. Example number B, we're going to letter that B, example letter B. 1 to infinity 1 over x to the 1/2 dx is equal to the limit as b goes to infinity of 1 over b, 1 over x to the 1/2, 1 to b of 1 over x to the 1/2 dx, which is the limit as b goes to infinity of the definite integral from 1 to b, x to the negative 1/2 dx due to simple anti-differentiation. We're going to get the limit as b goes to infinity of 2x to the 1/2 b, evaluate b at 1, and so that is going to equal 2 square root of b minus 2 square root of 1. And again, we notice as b goes to infinity, the square root is going to grow also. So therefore, I've got this is going to diverge. This limit will diverge. Does not have a limit, goes to infinity. B goes to infinity. So what do we know about the improper integral right there? So we're there. So we know that the improper integral from 1 to infinity of 1 over x to the 1/2 dx diverges. Example number 3, or example C, if you will. Look at the improper integral from 1 to infinity of 1 over x squared dx. And we see that that is going to equal, the limit as b goes to infinity of the definite integral of 1 to b, 1 over x squared dx. Again, so that I can anti-differentiate it. Limit as b goes to infinity 1 to b, x to the negative 2 dx. Anti-differentiate that guy right there, and I get the limit as b goes to infinity of negative 1 over x, evaluated from b to 1. Fundamental theorem of calculus right there. And what do I have right here? So this is going to be, negative 1 over b plus 1. Minus negative makes that a plus right there. And as b goes to infinity, this rascal here goes to 0. Negative 1 over b goes to 0, and 0 plus 1 is 1. And what does that tell us with respect to the improper integral? That tells us that this guy right here, the improper integral from 1 to infinity 1 over x squared dx converges. And all we care about it, we know it converges to 1, but we're going to say, all we really worry about today is that this rascal converges. So I've got this guy converging. I've got this improper integral diverging. 1 to infinity x to the negative 1 over x to the 1/2, yeah. And I have this dude right here, the improper integral from 1 to infinity 1 over x dx, also diverging. So where are we going to go with that? What we're going to do now is we're going to look at this dude right here, the integral test for series. And we can use this integral test anytime that's applicable. And so let's examine the hypothesis of the integral test for series. This is also a test that we will use to determine whether a series diverges or converges also. So let's look at the hypothesis. Here's the hypothesis. If f of x is a positive and decreasing, if f of x is positive and decreasing, for some x such that x is greater than or equal to some n, where n is a positive integer. That's the first part of the hypothesis of this theorem. If f of x is positive and decreasing for some x, where x is greater than or equal to some integer, some positive integer. And here's the second part of the hypothesis. And I have a sequence that is equal to f of n. A sub n is equal to f of n for some n greater than or equal to this n we're talking about here. And when we first talked about sequences, sequences are the same. What this says is that the output of this sequence and the output of these functions for these n integers are the same. They're the exact same. They have the same output there. And we've looked at that, and that's a fairly easy topic to think about. So this is the hypothesis for the integral test. F of x is positive, decreasing, and it's equal to some sequence for some n, positive integer, then this is the case. The series from n to that n, the summation from n to infinity of a sub n, and the improper integral from n to infinity of f of x dx, this series and this improper integral, they both diverge or they both converge. That's a nice theorem. It's a very nice theorem because keep in mind what one of our original statements when we started talking about series was, does the series converge or does it diverge? And we spoke a lot about, hey, you know what? We may not be able to find out where the series converges to, but it's going to be important for us just to determine if it does converge or diverge. So this is a nice theorem, the integral test for series. So how are we going to use that? Well, let's look at this guy. Let's look at that series. I'm looking at that. Oh, from n equals 1 to infinity of 1 over n. Does that thing converge or diverge? Converge or diverge? Let me step out again. Converge or diverge? Well, that dude diverges. Why does it diverge? Because we saw in a previous slide the improper integral from 1 to infinity of 1 over x dx diverged. We proved that with example A for improper integral. So now I know this guy diverges because of the theorem, the integral test, the improper integral test for series. This guy I know diverges, and if this guy diverges, this guy has to diverge because of that theorem. We proved those theorems. We proved those theorems in advanced calculus. I don't think this would be too difficult to prove. Let's go to our next example. Oh, before I go to the next example, hey, we got a piano up our nose. We better talk about our piano being up our nose. This is the most famous divergent. This series right here, the series from n equals 1 to infinity, 1 over n, this is the most famous divergent harmonic series. Must have something to do with some harmony. And I will let all of you famous musicians or famous musicians to be to discuss this harmonic series more in your music theory classes. Hopefully you will. So this is going to be a very this is one that we're going to remember. We know what 1 plus 2 is 3. We know what 1 plus 2 is 3, and we're going to know that this series right here is a divergent series, and it's the famous divergent harmonic series. Let's go to that second example, that guy right there, from 1 to infinity. The series from 1 to infinity of 1 over n to the 1/2. Does it converge or diverge? Think about that for a moment, converge or diverge. Young lady in the back, what do you think? You think, oh, you are absolutely right. That guy right there diverges also, since, oh, we did this. This improper integral from 1 to infinity of 1 over x and 1/2 dx, that rascal diverges. And by that integral test, if this guy diverges, because these are the same, if n is greater than 1, they have the same output. This guy no diverges, therefore this guy diverges. That series diverges. And this is positive, and it's decreasing. Positive and decreasing. Same output as this. So we're good. We can use that integral test for series. Example 3, or C, if you will. We'll let the gentleman in the back row over here determine whether this series converges or diverges. The series from 1 to infinity of 1 over n squared. Does it converge or diverge? Young man in the back row is thinking about this. Please, hands down. No shout outs. Here we go. Here we go. What do you think, young man? Oh, yes, you are correct. That sucker converges. Why does it converge? Because this improper integral converges. And we better check. Hey, this function is positive. It's always positive. It's always decreasing. And these guys here have the same, this sequence and that function have the same output for when n is greater than 1. Same output, so I can use the integral test. And I know this thing converges because of that simple little discussion example I had about improper integrals. So this converges, therefore this converges. Nice. Nice. So where does that lead us? That leads us, ladies and gentlemen, to this dude right here, the P-series test. And this is where we were going. This is what we wanted with this. Was our primary objective today. It was the P-series. Oh, so let's look at this. They call it the P-series because this is the exponent of that n. And if I go back, let's go back for a moment. Sorry. Let's go back. Hey, what is the exponent here? What's the exponent of x? I have x to what power? This is my improper integral example. Oh, I have x to the, make note of that. That here I have x to the 1 power. Right? And what exponent do I have here? What's the exponent of this rascal, this function? I have 1 over x to the 1/2. And 1/2 is what? 1/2 is, that's right, 1/2 is less than 1. So what about this guy right here? This function right here, 1 over x squared. And 2 is, you're correct, 2 is greater than 1. So I have an exponent greater than 1, I have an exponent less than 1, and I have an exponent of 1 here. So that brings us back down here. I don't want to go too far. Divergent, yes, divergent. I want to go down to the P-series. You tell me, you fill in the blank. The series from n equals 1 to infinity of 1 over n to the p, this diverges when what? You fill in the blanks. Pause the video. Now we're back. this thing diverges, you are correct. When P is less than or equal to 1, this guy is going to diverge. This is an easy test to prove. We didn't really prove it, maybe we verified it on those 3 examples of improper interval. We had to use the integral test though, of course. And here, hey, when does it converge? When does this series converge? It converges when P is greater than 1. So the series from 1 to infinity of 1 over n to P diverges when P is less than or equal to 1, and it converges when P is greater than 1. It's not too, doesn't have many applications just at the P-series itself, but like I said at the very beginning of the video, the primary application of the P-series is the direct comparison test or the limit comparison test. And we're going to take a series that we know diverges or converges and compare it with another series. These tests are for another video or another lesson. Thank you very much. And all I can leave you with, ladies and gentlemen, is pianos up your nose.